Math Blast 19. I can solve problems interpreting remainders. Baseball signups were held over 3 days. Friday, 21 players signed up. Saturday, 13 players signed up. And Sunday, 27 players signed up. If the rules state 9 players must be on the field during games, what's the greatest number of teams that can be made? First off, I want to determine how many total players signed up. So I'm going to add the 21 players from Friday, 13 players from Saturday, and 27 players from Sunday. I have 11 ones. I'm going to bundle 10 of those and make a greater unit. I have 6 tens. And so we have 61 total players that signed up. Now we want to take those 61 players and divide them into groups of 9 players. And that will tell us how many teams we're able to make. Now I can think of this as a number bond problem as well. I start with 61 and I'm going to make groups of 9. So I have 9, 18, 27, 36, 45, 54, and then I would have 7 left. Now those 7 are not going to make a team. Our teams have to have at least 9 players because there need to be 9 players on a field at a time. So the little asterisks represent my teams that I would be able to have. There are 6 teams with a remainder of 7 players. So we would say that 6 teams can be made. Now, if we were to interpret that remainder of 7, that 7 represents 7 extra players. Those 7 players would just be distributed among the teams that are already made. I can round to the nearest specified whole number. Round 42,536 to the nearest 1,000. Show your work. Since we're rounding to the nearest 1,000, I want to ask myself how many thousands are in my number. And so if I just look at the thousands place, there's a 2 in the thousands place. But if thousands is going to be my greatest unit here, I want to take everything to the 2. Everything up to that 2, that thousands place. So those 4 10,000s can be decomposed into 40,000s plus the 2 that's already in that thousands place. So in other words, we have 42 thousands in our number. And so that's going to be the bottom of my vertical number line as I round here. 42 thousands make up the number right now. In standard form, that's written as 42,000. If I were to add one more 1,000, we would have 43 thousands. That will be the number at the top of my number line. In standard form here, it is 43,000. The number that lies right between 42,000 and 43,000 would be 42,500. And in standard form, we write that as 42,500. Now, I want to place my number on the number line, 42,536. I know it's going to be right above this midpoint here. I'm going to put it right here, 42,536. Now I can determine if my number is to round down to 42,000 or up to 43,000. Whenever the number lies on or above the midpoint, it's going to round up. If the number were to lie below the midpoint, it would round down. So our number is going to round up to 42,000 or 43,000. Again, 42,536 rounds to 43,000 when rounding to the nearest 1,000. I can solve word problems involving addition and subtraction of fractions. There are 2 pies on the table that are the same size. I'm going to start with that. Here are my 2 pies on the table that are the same size. Now the first pie has 3/8 eaten, the second pie has 2/8 eaten. So here, eighths is our unit. I'm going to break each of my pies into 8 equal parts. In the first pie, I'm going to show 3/8 eaten. So I'll put an X on the pieces that are eaten. In the second pie, I'm going to show that 2/8 are eaten. So I'll put an X on those 2 of the 8 pieces. Now, that shows me that I have 1, 2, 3, 4, 5 pieces out of the 8 pieces that make the whole pie left. 5/8 is left here. In the second pie, I have 1, 2, 3, 4, 5, 6 out of the 8 pieces. So 6/8 of that pie is left. So if I add those together, 5/8 plus 6/8, I get 11/8. And 11/8 is the same thing. I'm going to use a number bond up here to represent this. 11/8 is 8/8, which would be a whole pie, and 3/8 more. So 11/8 is the same thing as 1 whole pie and 3/8 of another pie. That's what would be left. I can multiply a fraction by a whole number. Write an addition expression using unit fractions to represent the shaded portion of the tape diagram. Okay, so in order to figure out the unit fraction is the smallest fractional part in the whole. So when I look at the whole here, and the whole is represented by this bracket showing 1. This is the whole. I have 1, 2, 3, 4 pieces, 4 equal pieces that make up that whole. So each one of those pieces is worth 1/4. Each piece in our tape diagram here is 1/4. Now, when I put those together, I can add these unit fractions. 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 and get 5/4. So we know that's 1 whole and 1/4 more of another whole. Write a multiplication equation for the shaded portion of the tape diagram. Well, we would have 5 groups of 1/4, which equals 5/4. Now, I want to represent the bottom, the equation piece with the equal part. In terms of the expression where they wanted us to write an addition expression, I'm going to want to take this 5/4 away. I just wrote that to help me show the answer here. But in terms of the question, we were only asked for an expression, so we're going to take that away now and leave it as just the addition of the unit fractions. And then the multiplication equation is representing the equal sign and the total amount. Okay, so that's the difference between an expression and an equation. An expression just has your numbers and operation symbols, whereas your equation is representing or relating two expressions with an equal sign here or some relation symbol. I can classify triangles by sides and angles. Identify the triangle by sides and angles. So here, when I look at the sides, I notice that I have 2 equal sides. And so this is going to be an isosceles triangle. An equilateral triangle has all equal sides. An isosceles triangle has at least 2 equal sides. And a scalene triangle has no equal sides. So I'm going to call this isosceles. And in angles, in terms of angles, I see that we have this right angle here. So it is going to be a right triangle. A right triangle has a 90-degree angle. An acute triangle has all acute angles, meaning all the angles are less than 90 degrees. And an obtuse triangle would have an obtuse and an angle that measures more than 90 degrees but less than 180 degrees. In this case, the most specific name for our triangle is an isosceles right triangle. That's all for today, math friends.